Hello everyone and welcome to my channel. In this video I would like to have an overview of the make-do policies and variexec in FreeBSD. Okay, let's do this. We first start with the make-do policy. The make-do policy is a policy to allow unprivileged users to change process credentials. It supports per jail configuration. The overall effect is similar to sudo or to do-as. The policy is written as user ID equals the first user ID that the policy applies to, or the group ID, with followed by a bigger than sign, and then what I call change. And we're going to see about the change, and you can glue several of these policies together with semicolon. The change means that you go from for example, from the user ID 1 or from the group ID 1 into another user ID. So it would allow to change from one user ID to another user ID. It can go to another group ID, or you can have additional group IDs, or you might signal that the current group IDs must be kept, or that the current group IDs of the original user, cannot be kept. You can change several of these changes together with commas. For example, I could say that the user ID 1 goes to user ID 2, comma, another group ID. Let's see this in practice. So here I have a virtual machine that I just configured, completely new. It's freshly installed and only has Vim and Midnight Commander, because we all know Vim is the best text editor, right? All right, let's start. I also changed the default color background because you know already from a couple of videos from me, I don't like dark colors in the background. So black colors, they hurt my eyes. So I'm sorry. People complain about me using white colors as background. So let's try to find the middle ground here. I put gray. I hope everyone is happy. So let's start. I log in as root. And the first thing we need to do is we need to enable the make-do policy. For that, we're going to do sysrc-f bootloader.conf, and let's set make-do load equals yes. All right. And now we are just going to reboot the machine. Shutdown -r now. So let's log in again to the machine and let's do kld stat. And we can see that the make-do policy is on. Now I'm just going to show you that I've also pre-configured the two users, the user 1 and the user 2, just for demonstration purposes. And now let's let's allow the user 1 to become root. So for that, let's just, for the time being, do a sysctl security.make.do, and we see here that it's currently enabled, but there are no rules. So let's set the rules equals to what? Well, user ID 1001 can change to user ID 0, and with the group ID 0. That should be a good policy. We set the policy here. So let's see, the security make-do rules is set to user ID 1001 can change to user ID 0 with group ID 0, which means root. Now we have the mdo program, and let's switch to user root. Okay, actually, sorry, I need to log out and log in as user 1 because I was already root. So user 1 with password user 1. This is just for demonstration purposes. And here let's just see. So user 1 is not within any group, so it should not be allowed to change to root. It's not allowed. Sudo is not installed. Do-as is also not installed. Okay, but we have mdo installed, so operation not permitted. Very good. We want to become root, and let's try to execute bin sh. Well, it tells me that the operation is not permitted. Why is that? Because the policy tells me that the change needs to that I need to have the group ID 0, and I cannot keep my current group ID. So if I look at my ID, I'm currently in the groups 1001. So let's try again the same command and say that the additional groups should be empty. Hooray, I'm root. Who am I? I'm currently root. So this is an example of how to use McDo. Let's try another policy. So for this policy, I'm going to use sysctl security medium access control do. I currently have those rules, so I'm going to set rules equals, and let's add another one, UID 1001 going to UID equals 0, GID equals 0, and semicolon. Let's add the user ID 1002. Let's go for that. Goes to user ID 1001 with GID equals star. So this means that we allow the transition to any group ID, and we are going to allow GID to keep any thing. So here we are allowed to transition to any group ID, and we allow to keep all the groups. Okay, so the policy is loaded. Let's log out. So here I'm again as user 1, mdo, and let's go for user. So this is test 2. So we need to log in as user 2, and mdo user user 1, and let's just run sh and ID. I'm currently user 1. I changed from the user 2 to user 1, and there was no problem with the policies. Of course, this is very dangerous to allow the to keep any group, because let's just see here if we are again at user number 2. Actually, let's exit. Let's go to root. Let's see if the command is still there. Yes. Okay. We need to edit here. And let's build again the rule. So let's see first what is there, rules. And let's build up again the same thing. So user ID 1002, comma, GID equals, so actually I'm doing something wrong. Sorry for that. Let me log out. Let's go again to user 2 with user 2. And the command we had before was changing to user 1, and we could do this. And let's now tell that we want to be in the wheel group ID. Look, this is why it becomes very dangerous, because having a plus GID equals star just allowed the transition from user 1 to the user 2, and I'm placed now in the wheel group. So can I use SU? Okay, I was not able to change, but if I'm in the wheel group, typically I should be allowed to do an SU to root. The last thing I'm going to test, let's see here. Oops, not rot. So root. And let's load another policy. And this time I'm going to say that we are going from user, let's call it 2, to user ID 1001, but I want to keep the 1002. So I'm allowing the user with ID 1002 to become user 1001, but it needs to go to the group ID 1002, so it cannot change to the other ID. Let's confirm that this policy is loaded. So here it's there. So let's go to user 2 as password, mdo user test 1 with sh. Let's try it like this, and we should not be able to do it. It's not test1, sorry, user1. Operation is not permitted. But if we say we want to get the group test, in this case user2, we are still not able to do this because we would have additional groups. So we need to say the additional groups need to be empty. And now we are able to do the transition. And now you can see that I'm actually user1, but I am in the group ID of the user2. All right, so that's the principle of how the Mac policy, the MacDo, works. Now let's have a look at the policy for the veryexec. The veryexec policy is a policy based to lock down program execution based on the verification of digital signatures. It's similar to the macOS gatekeeper, if I'm not mistaken. There is a manifest containing all the signatures for all the programs that are allowed to run, and this manifest must be loaded into the FreeBSD kernel. Upon execution of the software, the checksum is computed. In the case we're going to see the SHA-256, and if the location of the program, if the full path matches and the signature matches, the program is allowed to run. Of course, only trusted manifests should be loaded into the kernel. And this is achieved, as we're going to see, by means of a trust anchor. The trust anchor that we're going to create is going to be with OpenPGP. And with OpenPGP, we are going to generate a private key and a public key. The private key, we're going to use it to sign the manifest. And the public key, we're going to use it to verify the signature of the manifest. We need a manifest file. The format for this file is the file name with a full path, space SHA-256 equals to the SHA-256 and some flags. The flags that are currently described in the main page is the indirect flag, the no FIPS, no bitrace, and trusted. Indirect means that the program cannot be run directly. Means, for example, you could run the program if it is in a shebang. An example for that would be an interpreter like Python that you'd not allow to run directly, but you'd allow it to run through a shebang. No FIPS means that the program is not allowed to be executed. I don't understand this policy very well. It's an explicit denial of run, but in any case, if the signature doesn't match, the program will not be allowed to run. The no bitrace does not allow the program to be debugged, and trusted means that the program is allowed to read from kernel memory under /dev/kmem. You might omit the flags, and it's just the program is just going to be allowed to run or not. After we write a manifest file, we take our private key and we generate a detached signature, the manifest.ask. This file can be used to verify that the manifest is trusted by the trust anchor. We have two additional components. Of course, we have the FreeBSD kernel, where we have the Mac policy, the Mac veryexec, and we have a program called veryexec, which when we're going to compile and we're going to see this, is going to include the public key inside the veryexec. So there is only one program when it's compiled in the system. There is only one trust anchor that can be accepted, and it is hard-coded and compiled into this program. This program is going to be used to load the manifest into the kernel and to turn on the policy enforcement. The FreeBSD kernel itself doesn't know about the trust anchor. What it basically has is when you load the manifest, it has the list of the files and the list of the checksums. Now, to load a manifest into the kernel, the first step we're going to do is we're going to take the public key, which is embedded in the executable, and we're going to verify that this digital signature actually checks against the manifest that we're trying to load. If this is successful, then we are allowed, then the program veryexec can load the manifest into the kernel. So after the signature is verified and the manifest is loaded into the kernel, we can finally issue the order to enforce the policy. Once this is done, the FreeBSD kernel is configured to enforce the policy. This means that when we try to execute a program, an executable, whichever it is, we're going to have a look at this program. So the FreeBSD kernel looks at the executable and checks against the database that it has the signatures, and it either matches or does not match. If it does not match, the program is not allowed to run. If it matches, the program can run. The interesting thing here is that all the libraries, the .so, the shared libraries, etc., they need to be signed. We cannot just sign the program, we need to sign all the libraries that this program depends upon. All right, so let's have a look at how we can make this in practice. Before we do that, one short comment. The very exec, you might notice that you don't have the very exec available in your FreeBSD system. And I looked in the kernel sources. We need to change a couple of things, and we need to compile this by hand. I'm going to show you the procedure slowly so that you can also repeat this by yourself if you want to do it. And once you have it done, you should be able to run the very exec yourself. So let's go back to the machine. And in this case, let's exit. We're testing the MacDo. So let's log in as root again. And for this case, we're going to go at the bootloader.conf and let's take out the MacDo. All right, so the next step is you need to install a FreeBSD system with /user/src. So the kernel sources must be available. Let me just turn on the lsSG because it looks a little bit better. And let's start patching the files. So the first file that we're going to patch is going to be the lib/libsecure. So libsecure boot, and we're going to go to the OpenPGP. Let's go to the makefile inc. And here we have the TA ask list, and we're going to patch this thing here. So we're going to write $. Okay, so here you can see the line that you need to change, and this file only needs this change. Now let's have a look at the next file we need to change. This is the OpenPGP key. And here we're going to go to this include, and we're just going to say include ta.h. So this is the line that we need to add, and we should be good to go. Then let's go one folder up, and let's edit the folder, the file localtrust.mk. And here there is the VE self-tests. This is for the FIP. So let's just say no. Let's change this to no. Now the makefile.inc, we're going to go to the section where it says ta.h. This is the part that we need to redo. And let's change this to ta_ask.h. And for this part here, we can just remove these lines and we can add our own. We can just say echo/include ta_ask.h going to the .target. So echo include ta_ask to target. There is only one small problem here, so which is we have two bigger signs. We should not have that, but let me just first copy this line and go here and get a single bigger than, and the second line has to have two bigger than signs. Now we go here and we say hash define trust anchor str as null, and we should be good to go. Another file we need to edit is /user source spin very exec, and let's edit the makefile. And here we're just going to write mk very exec equals to yes, and k pair SSL equals to yes. All right, so now all the changes that we need are basically done. Let's start creating the trust anchor. For that, we need to install a new privacy guard. Let's go first to the root directory and let's create a new key, gpg open pgp quick generate key patch pass phrase nothing with, let's call this the trust store, and it should be an RSA key. All right, so the key is created. Let's just check gpg open pgp list keys, and we have the key which starts with 688b something. Now we need to have the public and the private key. So let's just put here in this folder. So gpg open pgp export, and it has to be armor to trust anchor root ask. So we get this key, and here .sec, this is going to be the private or .priv as you want to call it, and export secret keys. So it's basically there. So let's have a look at TA root ask. So here you can see this is the PGP public key, and I can just show you the secret key. It doesn't matter because I'm going to throw this key away, and this would be the private key that we're going to be using in this example. So the next thing we're going to do is before we compile the very exec for the kernel, we are going to create the manifest, and for that I'm going to do something a little bit bad. It's just for an experiment. I'm going to use the find command to find all the files in the /bin /sbin /userbin, etc. And I'm going to create the SHA-256. So let's first find the very important is the libexec. So we get these two files, the user libexec. We also need these additional files. We also need libraries here. Let's take in /sbin. Let's take from bin /userbin. What else could we take? User lib. I think that should be it. So we get quite a lot of files, and not all of them are actually files that we should be looking at. So we're going to search for the type F, which is a file, and we're going to look if the file is actually an ELF file. So for that, we're going to execute, because we don't know the file extension. Some of them might be ELF files, some of them not. So we are going to execute sh-c and file, and here we're going to ask for this file type and do something like this. So this is, let's just first try it out. So here you can see, I just stopped. So we see that some of them are ELF, some of them are ASCII text, etc. And we don't need to sign the ASCII text files. Okay, so I was having a little bit of problems with the find command, and I just fixed it a little bit like this. So we're going to do the find the same as before, and then have the execution. I'm going to ask for the file type. I'm going to grab for the ones that have ELF, print the first column, and remove the semicolon. So when we run this, we get the file names, which are ELF. And let's just pipe this to SHA-256. All right, so it did the SHA for everything, and this is why I like to run step by step. We need here xargs, and now we should start getting the SHA for each file. And yes, we do. Now let's just pipe this into manifest, and let's look at the manifest file. And here we are. here are all the files that we need. So, but how many lines do we have? Let's see, WC manifest. There are currently 3,784 files here. So the other thing is that so let's have a look at head manifest. The manifest is not in the format of the manifest file that we need, and for that there are two ways to do this, or there are more ways to do this. I could do everything with Vim, or I could do the things with sed. Let's try very quickly to do the things with sed. So sed, let's search for, I think it's like this, SHA-256 space, and let's replace this with nothing for now. So let's just type in head manifest and pipe it into sed, and you can see that we are starting to look pretty good. And the next thing is going and replacing. Let's put again into sed-e. And we need to do the closing brackets, space equal. So search for this part. I think we still need to put this thing here and replace with SHA, not shared, SHA-256 equals to that with this one here. And lo and behold, it looks much better. So let's make this manifest.ok. And let's have a look at manifest.ok. Yeah, and the format looks good. So it's the name of the file and then SHA-256 equals something. Here we could put the flags afterwards, but we are not going to need that. So instead of the head, now we're going to do the entire thing. So cat instead of head. Cat and wc-l manifest.ok. And we have the same line. So manifest.ok is the file. It's the manifest that we need. So let's move manifest.ok to manifest. So now let's compile the kernel part. So user src. Let's start with the libs, and we are going to start with the lib bear and make install. Now we need another one, so we go to lib very.exe and make install. Now we need the lib secure boot, and we're going to type in make, but it's going to say, hey, you need the trust anchor, but we generated the trust anchor, so we just need to copy the TA ask file here. That's it, and now we compile and make install. All right, we are almost there. Now, user src spin cd very.exec make install. So this was the steps required to compile the executable, the very.exec. And if you remember, I was saying before that this executable contains the public key embedded inside. So let's just confirm this. Let's see which very.exec. Okay, make install. Did I install it before? So which very.exec, and yeah, spin strings spin very.exec, and well, let's just search for begin, and we see here begin PGP public key block, so it's embedded there. Now we need to compile the kernel drivers, so we're going to go to user src sys modules, and we need to go to the very.exec module, make install. We need the Mac very.exec make install, and the Mac very.exec SHA-256 make install. Finally, we need to enable those modules. So in the bootloader.conf, currently we don't have the macdo anymore, but we can do sysrc on the file bootloader.conf. Let's start with the Mac very.exec load equals yes. SHA-256, load yes, and the module very exec. All right, I think this is looking good. Let's reboot the machine. Let's log in as root and kld stat. And we see here we have the Mac very exec, SHA-256, Mac very exec, and the very exec kernel module. Now we also have the manifest here. So let's first sysctl security Mac very exec. And we see that algorithms that are enabled is the SHA-256. The state is none. And yeah, this is not shown there, but the DB, the database, there are no fingerprints in our database. There is also, I forgot to sign the manifest. So let's sign the manifest with GPG-A detach signature on the manifest. And now we see that we have a manifest.ask. This is the digital signature for the file manifest. Let's try to load this. So first of all, before we do this, let's go to very exec. We see that the state is nothing. There is no state. Very exec on the manifest and verified manifest signed by the trust store. The trust store is the name we gave for the key. So, and now let's see, and the state changed to loaded. So we loaded the manifest into the kernel. Let's see in the database, we have all these things, all these neat things. Those are all the SHA-256 corresponding to the programs. Currently, it's not enabled. So if you remember, I did this on purpose. I didn't sign the binaries, which are under user local bin. So which Vim? So this is user local bin Vim. So let's see, Vim can start now. Okay. And now let's enable the signature. So, but before that, because there are some messages that will be popping up here and I don't want that. So I'm going to edit etc syslog conf. And I'm going to take this logging to the dev console. I'm going to take it out just to make sure that it looks nice. I'm just going to reboot the machine. You don't need to do this step. So we need to do some stuff again, which is load the manifest. So root, syslog, not syslog, syscontrol, security, Mac very exec is not there, but very exec on the manifest. It loads. And we have it loaded with the DB. Okay, so the DB is there, we reproduced. And now let's activate the thing. So very exec -c enforce. Now things are running. So syscontrol, which is a software, but it has been signed, the syscontrol. It shows that everything is fine here. And we see loaded, active, and enforce. Now let's try to run Vim. What do you think is going to happen? Vim is not signed in the manifest. Vim, authentication error. It's not allowed to run. If we look at the dmask, it says Mac very exec, no fingerprint for this executable. And that's it. Execution denied. Well, which VI? Well, it's in under user bin. Does it work? If you remember, I signed that one. So VI, yes, it works. So the system is pretty much locked down now. So let's have a look again at the manifest. So only these 3,000 and something files that are on my machine are really allowed to be executed. Interesting enough, the which PKG, let's see, which PKG user spin, I did not sign that one. So this is also authentication error. Which PKG static is also user local spin is also not signed. PKG static authentication error. So I cannot even install new packages. But the interesting thing again here is even if we would install new packages, they are not signed, they are not allowed to be executed. how do I revert this operation? Well, I reboot the system. Yeah, man is also interesting enough. Man is, I did not know about this before. Let's just say which man file user bin man. And it's actually an POSIX shell script. And if you remember, we looked at ELF files, and this is not an ELF file, therefore it's not allowed to run. Interesting, right? If we would add the user bin man to our manifest, then we would have this running. All right, and that's it then for today. I hope you enjoyed the video. If you have comments or suggestions, please use the space down below. Otherwise, thank you for passing by, have a nice day, take care, and see you next time. Bye bye!